All right, we're going to take a look at a couple alternate alternate definitions of a derivative. So this is a derivative at a single point. So you reviewed that from the last video. Let's do an example. So f of x is equal to x cubed. We're going to use the alternate form of derivative to find f prime of 3. Here we go. So we're going to say this is the derivative or the slope at a singular point. So we're going to use f prime of c, which is the derivative at c, is equal to the limit as x goes to that c value of your function. Basically, this is the slope, f of x minus f of c over x minus c. All right, let's go ahead. Remember, f of x is x cubed, so we're going to do f prime of, we're evaluating at x equals 3. So the limit as x approaches 3 of the function f of x, which I can write as, actually, I'll just write it, f of x minus f of 3. So the y value at x equals 3 over x minus 3. Time to substitute. So the limit as x goes to 3 of f of x, which is x cubed, and then minus, let's plug in the 3 in for x, so 3 cubed all over x minus 3. Okay, I know it's annoying to write all this stuff out, but remember, dropping the limit operator is like dropping a multiplication sign or an add sign, okay? So, or like a log or something like that, okay? So we're going to do x cubed minus 27 over x minus 3. Check it out. X cubed minus 27, that's a difference of cubes, or you can use your synthetic division to divide out the root from x minus 3. So what's the root from x minus 3? Well, it would be 3, so you can use your synthetic division there. I like difference of cubes. So the difference of cubes is a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. If you don't remember that, you can just look it up, but you're going to have to kind of know those. Difference of cubes and sum of cubes. Okay, now we'll factor. So f prime of c, f prime of 3, the derivative at x equals 3, is equal to the limit as x approaches 3 of x cubed. Nope, just kidding. We need to factor. So that's going to be so it's the cube root of x. So it would be x minus the cube root of 27, which is 3, times x squared plus 3x plus 9. Right? So this is basically my a value and my b value, and then I plug those in. Okay? All over x minus 3. I see that these cancel, and since the denominator, oh, look, my face is in the way. I'm going to move it. Okay, so see these cancel, and then I'm going to plug in or substitute in the 3, so direct substitute. And when you direct substitute, that's when you get to drop the limit operator. So I'm going to get 3 squared plus 3 times 3 plus 9. So I can see that I have 9 plus 9 plus 9, which is going to give me 27. F prime of 3 is equal to 27. So what does this mean? This is the slope, or the IROC, the instantaneous rate of change, at x equals 3 on the graph of x cubed, or f of x. Okay. So when x is equal to 3 on f of x, then the slope is 27. Fast rate of change. Okay, so when can't we take the derivative? Or what we say, when is a function not, my face is in the way again. Okay, so when is the function non-differentiable? So we know for these 3 graphs here at x equals a, the function is not differentiable. So it means you can't take the derivative. So there's 5 situations where we cannot take the derivative, and they are at a cusp, or a corner, which we're just going to call a sharp turn. Um, there are many different kinds of discontinuities that will give us non-differentiable points. So holes, jumps, and vertical asymptotes. And then also when we have a vertical tangent line in the graph. So sharp turns, holes, jumps, vertical asymptotes, and vertical tangent lines. Next up, let's consider, we're going to move to the bottom first, actually. Okay, so we're going to consider this graph. I know that I can see right now that it has a sharp turn because it's an absolute value function. So we have f of x is equal to the absolute value of x minus 2. First off, is it continuous at x equals 2? Yes. Okay, it is. So first off, to be differentiable, you have to be continuous. Second, we have to make sure that that a limit exists, and that so a limit exists. So what do we need for a limit to exist? That it has to matchy on the left and the right, right? The left and the right limits have to match. So let's check it out. Remember absolute value graphs? They are really just disguised piecewise functions. So on the left-hand side, this line here, left-hand side of x equals 2 is the equation negative x minus 2, and the right side can be defined by the equation x minus 2, right? It's just the positive and negative slope of the graph. So we're going to have to take a look at these left and right hand limits, so let's do that now. Okay, the limit as x approaches 2 from the left, and we're going to go ahead and say, what is the derivative at x equals 2? So I'm going to use my derivative at a point equation. So f of x is equal to minus f of c. So f of 2 over x minus 2. So derivative at a point. We're looking at the point, x equals 2. All right, I got the absolute value. Uh-oh, I did a big boo-boo. The limit as x approaches 2 from the left of the absolute value of x minus 2, because that's my function, minus what is the value of f of 2 right here? F of 2. F of 2 is equal to 0. So on the function, the y value is 0. So I'm going to subtract 0 over x minus 0. So I basically have, let's write out another step. The limit as x approaches 2 from the left. So from the left, I can drop the absolute value signs if I use this equation that models the line or the arm on the left-hand side. So negative x minus 2 over x minus 2. I see that those cancel, leaving me with a limit of negative 1. Does that make sense? What is the slope of this line, of the red line? It's negative 1. Okay, so again, the derivative is going to be negative 1. The rate of change is negative 1. Okay, on the right, the limit as x approaches 2 from the right of f of x minus f of 2 over x minus 2. Again, plugging stuff in. All right, the function is the absolute value of x minus 2 minus f of 2 is equal to 0, and then we're going to subtract x minus 2. I made a mistake up here. I accidentally put in a 0 when that should be a 2. My apologies. Okay, so I can see that's going to go away. Now I want to drop the absolute value signs. How do I do that? I need to use the equation on the right-hand side, of x equals 2, which is x minus 2. So I'm going to go the limit as x approaches 2 from the right of x minus 2, positive x minus 2, over x minus 2 is equal to, and I see those cancel, so that's going to give me a 1. The limit of 1 is 1. Okay, so what I get is, do the right and the left hand sides matchy matchy? So do the right and the left hand side limits match? No. So I get this situation. Okay. So the function f of x is equal to the absolute value of x minus 2 I said that weird, sorry. It is continuous at x equals 2, but the one-sided limits, or the left and right hand side limits, do not match. They know matchy matchy. I know. Thus, f of x is not differentiable at x equals 2, and that also means that we do not have a tangent line at the point 2 comma 0 on f of x. Okay. So if I go back to the graph, I technically cannot write a tangent line right here because there is none. The left and the right hand sides do not match. Okay, so to wrap things up, if a function is discontinuous or not continuous, is it differentiable? So no, it is. It is at some, probably is at some point. So we're going to say it is not differentiable at the point of discontinuity. Okay, so if the original function is continuous for all x values, is it always differentiable? Well, check out this absolute value graph. It's continuous for all values. Is it differentiable at all points? No. So not necessarily is our answer. Think about sharp turns and vertical tangent lines. Okay, lastly, if a function is differentiable, so if you have the derivative over all x's, what does that mean about the original function? It means that the original function is continuous. So if the original function, if we could take the derivative for the entire part of the original function, then we know, working backwards, that if we have the derivative, we know that the original function is also continuous for all points. Okay, bye.